Hello everyone, I'm the tutor in the math help room, and this was a video that was requested by one of your classmates. They wanted a little bit of a review of L'Hopital's rule. So, L'Hopital's rule states that if the limit as x approaches a of some function f of x over another function g of x, if that equals 0 over 0 or it equals infinity over infinity, then we can make an equivalent limit. So that same limit will then be equal to the limit of the derivative of the numerator over the derivative of the denominator. And again, in order to use this equivalency, we need to have it in the form of 0 over 0 or infinity over infinity. Now there are a few different forms we'll be able to adjust. 0 over 0 and infinity over infinity are good to go. However, infinity times 0, infinity minus infinity, 1 to the infinity, 0 to the 0, and infinity to the 0 are other forms that we need to change to make 0 over 0 or infinity over infinity. So let's go ahead and take a crack at example 1, which is already in the form of 0 over 0. And we can, because if we took 1 and plugged 1 in for x, because this is the limit as x approaches 1, if we plugged in 1, the ln of 1 equals 0, and if we plugged in 1 in our denominator, 1 minus x, 1 minus 1, that's also equal to 0. So because we're in a form that fits that definition, we can go ahead and apply this rule, which states that we can take the derivative of our numerator, so I'll write this out explicitly, so we can take the limit as x approaches 1 of the derivative d dx of the ln of x, and put that over d dx, the derivative with respect to x of our denominator 1 minus x. So this is going to be equal to the limit as x approaches 1 of, well, this derivative of ln of x is 1 over x, so that's in our numerator, and we're going to put that over the derivative of our denominator, which 1 goes to 0, so a negative x, that derivative is going to be negative 1. So for our limit, we have the limit as x approaches 1 of 1 over x over a negative 1, so that's negative 1 over x. And if we plug in 1 for x, we'll get negative 1 over 1, which is equivalent to negative 1. So the limit of our function ln of x over 1 minus x, as x approaches 1, that limit is negative 1. Now in example 2, we can go ahead and jump right into this because we're in a proper form to where we can take the derivative of the numerator and put it over the derivative of the denominator. So you can see that if I plugged infinity in, I'd get infinity over infinity. So applying L'Hopital's rule to this, I'll just take the derivative of my numerator over the derivative of my denominator. So I'm going to take the limit as z approaches infinity of the derivative of my numerator is going to be 2z plus 3. And the derivative of my denominator is going to be 12z. So 2z over 12z, if I still plugged in infinity, or if we took the limit as z approached infinity, I would still get infinity over infinity, which is still in a form that I can continue to do L'Hopital's rule with. So there's not a limit to how many times we can take the derivative, just as long as we're in that proper form, infinity over infinity or 0 over 0. So again, let's do L'Hopital's. So the derivative of our numerator is going to be 2, and the derivative of our denominator is going to be 12. Now I no longer have z to plug in for, so 2 over 12 is the same as 1/6. So 1/6 is this limit in example 2. And we can confirm that because we know a trick for figuring out the limits at infinity. Highest power rule, right? What's really dictating the growth of that numerator is going to be this z squared, and what's really dictating the growth of the denominator is going to be this 6z squared. So we just need to look at those coefficients. Z squared over 6z squared, that's 1 over 6, so 1/6. And that was by the highest power rule. So you can see that repeatedly doing L'Hopital's will get you the same result. Now let's look at a different form. For this, we have 0 times infinity, which is technically an indeterminate form. So we're going to try to arrange it to get it into the form we want, either 0 over 0 or infinity over infinity. Now, when we have this multiplied together, remember, dividing by a fraction is the same as multiplying by its reciprocal, but we're able to also flip that. So what I'm saying is that I can take this 3x and put it as a fraction in the denominator. And when I do that, I'll get the limit as x approaches infinity of the sine of 1 over x all over 1 over 3x. So you can see I didn't change the value of the function within my limit at all. I just put that 3x all the way down in my denominator and in the denominator of my denominator. So if I divided by its reciprocal, I'd still be right there at 3x times sine of 1 over x, which let's double check that we're in this form before we continue on. We plug in infinity for x, or as x goes to infinity. So plugging in infinity, 3x goes to infinity, and plugging in infinity for the sine of 1 over x, plugging it in for x, that's the sine of, well, the limit of 1 over x as x goes to infinity is 0, and the sine of 0 is 0. So there was our infinity times 0. And all I needed to do was to adjust one of those functions. Now, if I wanted to, I could have moved the sine of 1 over x all the way down into the denominator by doing 3x over 1 over the sine of 1 over x. That's also okay. When I do it this way, however, I'm going to get something a little bit different. So if you look at me plugging in or taking the limit as x goes to infinity, up here I get 0 over 0 now, because 1 over 3x as x goes towards infinity, that fraction gets smaller and smaller. Whereas if I take the limit as x approaches infinity, I'm going to get infinity over, well, we already said the sine of 1 over x as x approaches infinity goes to 0, and 1 over a number that's continuing to get smaller is going to get bigger. So that's infinity over infinity. 3x over 1 over the sine of 1 over x versus sine of 1 over x over 1 over 3x, they're equivalent, so it doesn't matter which one you choose to do. I always try to move the easier function, the function where I have to write less. So that's why I just moved that 3x and wrote it as its reciprocal in the denominator, as opposed to dealing with the sine function. So going back to what I originally started with, we showed that we have 0 over 0. And because we showed that, now we can take the derivative of our numerator over the derivative of our denominator, because we have 0 over 0. So when I do this limit as x approaches infinity of, well, the derivative of the sine of 1 over x is going to be some chain rule. So the derivative of the sine of something is the cosine of that function, so the cosine of 1 over x, but then I have to multiply by the derivative of what's inside. So 1 over x is like x to the negative 1. So if you envision taking the derivative of x to the negative 1, that negative 1 comes down in front, and then I decrease that exponent by 1. So that's negative 1x to the negative 2, or negative 1 over x squared. And that's all over, well, let's take the derivative of our denominator, which is like 1/3 times x to the negative 1, which the derivative of x to the negative 1 we've already done. So this is going to be 1 over 3x squared, and that's a negative. So negative 1 over 3x squared, or negative 3x to the negative 2, however you'd like to write it. So before we go ahead and start plugging in as x goes towards infinity, let's go ahead and simplify. Because this negative 1 over 3x squared, notice I have an x squared up here, so when I flip that fraction, I'm going to be able to cancel out that x squared. So as opposed to dividing by a negative 1 over 3x squared, I'm going to multiply by a negative 3x squared. And you can write that as a fraction over 1, if you like to keep it in fraction form. Otherwise, it's just negative 3x squared. And you can see that x squared cancels out with x squared. This negative times the negative will be a positive. So I'll get the limit as x approaches infinity of the cosine of 1 over x times 3, or 3 cosine of 1 over x. As x approaches infinity, 1 over x goes towards 0, and the cosine of 0 is 1. So 1 times 3 is 3. So the limit in example 3 is 3. Now in number 4, we have another indeterminate form. And this should read the square root of k squared minus 5k minus k. So notice that if I plug in infinity, I get infinity for this function minus infinity. And no, we can't necessarily use growth rates here because the square root of k squared minus 5k, we can't just distribute that square root to each of those terms. But if we can envision, this is going to have some power of k to the first as its highest power, and this also has the power of k to the first. But we're not exactly sure what that limit's going to be, so we're going to need to work it out. So you can see that we are indeed in the form of infinity minus infinity. And what we need to do is we need to manipulate or massage this problem just a little bit to get it to look like 0 over 0 or infinity over infinity. So what I'm going to do is I'm going to rewrite this limit, and the part I'm going to rewrite is what's underneath this radical. So k squared minus 5k, I want to be able to pull out something from within there. So I'm going to pull out a k squared from each of those terms. Pulling out a k squared from the first term will leave me with 1. And if I pull out a k squared from this term, I don't quite have k squared. So that's going to leave me with 5 over k if I were to pull k squared out of that term. And then I'm still going to be subtracting k. Now, why I rewrote the limit that way was so that now I can take that square root and apply it, because those two terms underneath my square root are multiplied together, so I can apply the square root to k squared and apply it to 1 minus 5 over k. So when I apply the square root to k squared, the square root of k squared is just k. So this will become k times, I'll leave the square root with 1 minus 5 over k, because there's no way to distribute that into this, because those two terms are subtracted. And then I still have minus k. If you notice, I have a k in this term and a k in this term, so I can pull out a k from both of those. So now I'm going to have the limit as k approaches infinity of k times the square root of 1 minus 5 over k minus 1. So you can see I pulled out k from this chunk and from this chunk to leave me with k times the square root of 1 minus 5 over k minus 1. So we're getting closer, because if you think about taking the limit now, I'm going to get infinity for k times, well, if this approaches infinity, 5 over k goes to 0, so I'll get the square root of 1, which is 1, minus 1, which is 0. So we're getting closer to the form. Now we have something where we have 0 times infinity, or infinity times 0, so this is where we can just move one of those down into the denominator. And let's move the simpler one. Let's go ahead and move k. So I'm going to rewrite this as the limit as k approaches infinity of the square root of 1 minus 5 over k minus 1, and that's all over. I'm moving this k into the denominator, but I'm not changing what this limit's equal to. I'm just putting 1 over k in that denominator, which is the same as having that numerator multiplied by k. I'm just moving this k into the denominator as a fraction. That's because now if I took the limit as k approaches infinity, my numerator would equal 0 and my denominator would also equal 0. So this equals 0 over 0. Now we can go ahead and take the derivative of the numerator and put that over the derivative of our denominator. So I'll do the limit as k approaches infinity of the derivative of my numerator. Well, this 1 that's subtracted goes to 0, So I'm just going to have to chain rule that square root. So I have 1/2 bringing that exponent down because the square root is something raised to the 1/2. Keep that inner function, and that goes to the negative 1/2 times the derivative of that inside, which the derivative of negative 5 over k is going to be a positive 5 over k squared, because this is negative 5 times k to the negative 1. Bring that negative down in front, that's 5k to the negative 2, or 5 over k squared. So that's my numerator, and my denominator, the derivative of that, sorry, I'm running a little bit out of room here, but I think we'll make it with this problem. The derivative of 1 over k we know is negative 1 over k squared. So you can see that if I was to flip this fraction up, this k squared would cancel out with this k squared to leave me with the limit as k approaches infinity of 1/2 times 1 minus 5 over k to the negative 1/2 times 5. So I'm going to write that as 5 all over 2 times the square root of 1 minus 5 over k. So what I did is I just moved this negative exponent in the denominator as a positive exponent, so the square root. That chunk to the positive 1/2. And remember, this negative did not get canceled out in my denominator, so my overall fraction is negative. So what's left within here as k approaches infinity? 5 over k goes to 0. So I'm left with negative 5 over 2 times the square root of 1 minus 0, or the square root of 1, which is just 1. So this is negative 5 over 2, or negative 5/2, as my solution in example 4. Now for example 5, 1 to the infinity, which if you're using this as a Calc2 review of L'Hopital's rule, this is going to come up a lot when dealing with series and sequences. So if we're in the form of 1 to the infinity, the exponent is what's giving us an issue here. So we need to take that exponent and move it down in front, but we don't want to change the overall value. So what function allows us to drop an exponent down in front? That's the ln, right? But I need to make a note to myself that I'm applying the ln to my function. What essentially cancels out an ln? That's going to be an e to the ln. So I like to make a note that this is going to be equivalent to e to the l. And what I'm going to need to solve for is l. And l is going to be equal to the limit as z approaches infinity of the ln of 1 plus 3 over z to the z. Now I applied that ln again because it allows me to drop this exponent down in front. So we have z times the ln of 1 plus 3 over z. So if we think about taking the limit as z approaches infinity, what form are we in? Well, we have infinity times 3 over z goes towards 0, ln of 1 is 0, infinity times 0. So we're close. We just got to move something into the denominator. So let's move that easier chunk. Let's move z. So we're going to write this as the limit as z approaches infinity of, and what I like to do, just so I don't forget, I'm going to also say this is what L is equal to, not my overall limit of my original function. This is just my L. So I'm going to have the ln of 1 plus 3 over z all over 1 over z. Again, I'm just moving that z all the way into the denominator as a fraction. And that's because that allows me to have 0 over 0. So now I can take the derivative of my numerator and write that over the derivative of my denominator. So L is going to be equivalent to the limit as z approaches infinity of the derivative of the ln of some function is 1 over that function. So we have 1 over 1 plus 3 over z. And then that's going to get multiplied by the derivative of that inside, remembering our chain rule. The derivative of 3 over z is going to be negative 3z to the negative 2. Or you can write it as a positive exponent as negative 3 over z squared. I'll leave it as a negative exponent just to show you that ultimately in the end it won't matter. And that's all over. We're going to put that over the derivative of our denominator, which the derivative of 1 over z is negative z to the negative 2. So you can see that my z to the negative 2's will cancel out, and this negative will cancel out with this negative, because a negative over negative will be a positive. So my limit L is going to be equal to 3 all over 1 plus 3 over z. And that's the limit as z approaches infinity of that function. And as z approaches infinity, 3 over z goes towards 0, so we'll be left with 3 over 1, which is just 3. But remember, that's what L is equal to. So our overall limit is e to the L, which is e to the 3. That is our solution for the limit as z approaches infinity of 1 plus 3 over z to the z. Moving on to number 6, and the limit of x to the x as x approaches 0 from the right is a classic example of the form 0 to the 0. And again, that exponent is what's giving us an issue, so we're going to apply the ln. So this, I'm going to make a note, is equal to e to the L. So my L then is going to be the limit as x approaches 0 from the right of the ln of x to the x, which that x in the exponent can be dropped down in front. So from here, if I were to approach 0 from the right, the ln of x as we approach 0 from the right goes towards infinity, and x is just going to go towards 0. So this is in the form of 0 times infinity, or infinity times 0. So we're just going to move something into the denominator so that we're set. So I'm going to take the limit as x approaches 0 from the right, making a note that this is what L is, of the ln of x over 1 over x. So now we have infinity over infinity. So let's take those derivatives. L is going to be equal to the limit as x approaches 0 from the right of the derivative of ln of x is 1 over x, and I'll put that all over the derivative of 1 over x, which is negative 1 over x squared. So flipping that up, we'll get the limit as x approaches 0 from the right of negative x squared over x, which negative x squared over x is going to be a negative x. Simplifying that down, and if we're plugging in 0 for x, that just goes to 0. But remember, this is what L is equal to. So our overall limit is going to be equal to e to the 0, which e to the 0 is 1. So 1 is our solution for example 6. And lastly, example 7, infinity to the 0. This one also comes up a lot when dealing with series and sequences. So if I do the limit as k approaches infinity of k to the 1 over k, that's infinity to the 0. Again, the exponent's what's giving me issues, so I'm going to apply a function that allows me to drop that down in front. And that function is the ln. So I'm going to make a note so I don't forget that this is equivalent to e to the L. So if you have to star it, circle it, something, don't forget to go back to that e to the L, where L is now going to be the limit as k approaches infinity of the ln of k to the 1 over k, but dropping that exponent down, 1 over k times ln of k is the ln of k over k. So you can see we're already in such a nice form. ln of k as k goes towards infinity is infinity, and k as k goes towards infinity is also going to go towards infinity. Boom. All we got to do is take the derivatives. So L is going to be equal to the limit as k approaches infinity of the derivative of ln of k is 1 over k, all over the derivative of k, which is simply 1. 1 over k over 1 is going to be the limit as k approaches infinity of 1 over k, which for this we get 0. Now this is what L is equal to, so overall we get e to the 0, which again is 1. So 1 is our solution for the last example in this worksheet. Now this was me running through a couple of the different forms that might possibly come up. And I will say that you will probably see k to the 1 over k in a couple examples for series. Or they could say, hey, k to the 3 over k, which k to the 3 over k is really k to the 1 over k cubed. I believe this might have been one of your homework questions. But remember, we know what this limit is. The limit of k to the 1 over k we just showed equaled 1. And 1 cubed is still just 1. So that's a helpful hint. I would just make sure you have the limit as k approaches infinity of k to the 1 over k memorized, since it's something easy to memorize. But don't fret if you don't remember it. Just do L'Hopital's rule. So hopefully you found this review helpful. If you have any more questions, as always, leave them in the comments below. And see you in the next video.